CIET NCERT presents audiobook Curiosity, Textbook of Science for Grade 7.
Page number 105, Chapter number 8, Measurement of Time and Motion. On the right-hand side of this page, a QR code is given, on scanning to which you can access the other resources related to the chapter. Prerna and her younger sister are watching a sports channel on television. Prerna enjoys running and she has been declared the fastest runner among the girls in her district for winning the 100-meter sprint at an inter-school competition held at the district level. She is now training to compete at the state level. She dreams of representing India at the international level in 100-meter sprint contest in future. While watching the rerun of sprints at the Olympic Games held in the past, Prerna is always amazed that the measurement of the time taken for the race is so advanced that they could identify the winner even when two sprinters seemed to cross the finish line almost together. However, in her school, the sports teacher only used a special kind of watch called a stopwatch for timing the school races. She had noticed her mother wearing a watch on her wrist and her sister looking at her mobile phone when she needed to check the time. Her uncle used a braille watch and had recently acquired a talking watch that announced the time at the touch of a button. There was also a large clock on the wall near the school entrance. Her thoughts turned to people in the ancient past who did not have the modern gadgets we have today, and she wondered. Children, at the bottom of this page, a picture is given. In this picture, 7 schoolgirls are running on a track in a school playground. Teacher and other students are watching from both the sides. A sport teacher is also standing here and holding a stopwatch for recording the time taken. Page number 106. On the top of this page, there is a dialog box with a picture of a girl who is asking, how was the time measured when there were no clocks and watches? 8.1 Measurement of time. Humans got interested in keeping track of time long ago. They started noticing that many events in nature repeat themselves after definite intervals of time. For example, the rising and setting of the sun, the phases of the moon, and the changing seasons. They started using the cycles of these events for timekeeping. First, they devised calendars. A day was defined by the cycle of rising and setting of the sun. Then began the quest to find ways of knowing the time of day. So, they made many devices which helped them to measure smaller intervals of time within a day. Some of these were sundials, water clocks, hourglasses, and candle clocks. At the left-hand side of this page, some figures are given. Figure 8.1, a sundial is given. Figure 8.2, a water clock. A. Water flowing out type. B. Floating bowl type is given. Figure 8.3, an hourglass is given. Children, at the left-hand side of this page, some figures are given. Figure 8.1, a sundial. A sundial is represented as a flat circular platform with a stick in the center. The shadow of the stick moves as the sun changes position. Figure 8.2, a water clock. A. Water flowing out type. A pot with water dripping slowly through a hole at the bottom. The pot has markings on the side showing how much time has passed. B. Floating bowl type. A ball with a small hole at the bottom is placed on water. It slowly fills up and sinks after a fixed time. Figure 8.3, an hourglass. An hourglass has 2 glass bulbs connected at the neck. Sand flows from the upper bulb to the lower one. When the bulb is empty, the time interval is over. Figure 8.4, a candle clock. A candle with markings along its length is given. As it burns down, each mark indicates a unit of time passed. In a sundial, time is determined with the changing position of the shadow of an object cast by the light of the sun during the day, as given in figure 8.1. The water clocks use the flow of water out or into a vessel to measure time. In one type, water flowed out from a vessel which had markings for time, as given in figure 8.2a. In the other type, there would be a ball with a fine hole at the bottom which was floated on the surface of water, as given in figure 8.2b. It gradually filled up in a fixed time and finally sank. Then it was lifted up and floated again. In an hourglass, which is given in figure 8.3, time was measured on the basis of the flow of sand from one bulb to another. Candle clocks, as given in figure 8.4, were candles with markings that indicated the passage of time when burnt. Page number 107. Children, let's go through an interesting box here named as Fascinating Facts. It is given at the top of this page. It highlights fun facts, interesting observations, and curiosity-driven questions. This box reads, the world's largest stone sundial and Samrat Yantra was built around 300 years ago at the Jantar Mantar in Jaipur, Rajasthan, a UNESCO World Heritage Site that houses several astronomical instruments. With its imposing height of 27 meters, its shadow moves at about 1 millimeter per second and falls on a scale finely marked to measure time intervals. With its imposing height of 27 meters, its shadow moves at about 1 millimeter per second and falls on a scale finely marked to measure time intervals as short as 2 seconds. Like any sundial, it measures local or solar time, requiring a correction to determine Indian Standard Time. The picture of Samrat Yantra is also given in this box. Should we make a simpler water clock? Activity 8.1. Let us construct. Step 1. Take a used transparent plastic bottle, half liter or larger with its cap. Step 2. Cut it into two, roughly in the middle, as given in figure 8.5a. Step 3. Using a drawing pin, make a small hole in the cap of the bottle. Figure 8.5b. At the middle of this page, figure 8.5 is given, which represents making a simple water clock step by step. Step 4. Place the upper part of the bottle in an inverted position over the lower half, as given in figure 8.5c. Step 5. Fill the upper part of the bottle with water. You may add a few drops of ink or color to make the water level easily visible, as given in figure 8.5d. Step 6. The water will start dripping into the lower part of the bottle. Using a watch, mark the level of water after every 1 minute till all the water drips down. Your water clock is ready. Can you now guess how to use it? Pour the water from the lower part back into the top part and watch the level of water dripping into the lower part. Every time it touches a mark made by you, 1 more minute has passed. Page number 108. At the top of this page, an interesting box named as Fascinating Facts is provided. Let us read it. In ancient India, time was measured using both shadows and water clocks. The earliest reference to shadow-based time measurement appears in the Arthashastra by Kautilya, was composed and revised between the 2nd century BCE to 3rd century CE. An accurate expression for time in terms of the shadow of a vertical stick was given by Vrahmihira around 530 CE. The water clock with water flowing out was described in Arthashastra, Sardula Karna Vadana, and some other texts, early CE centuries. These clocks were not very accurate because as water levels dropped, the flow rate decreased. This led to the development of the sinking bowl water clock, which is given in figure 8.2b, or Ghatika Yantra, first mentioned by Aryabhatta and then in several astronomical texts later. Time was measured constantly with Ghatika Yantra at Buddhist monasteries. royal places, town squares, and each time the ball sank, it was announced by drums, conch shells, or striking a gong. Though the Ghatika yantra was progressively replaced by pendulum clocks in the late 19th century, it continued to be used at the religious place for rituals. As human civilization advanced and as people began to travel long distances, the measurement of time became very critical. This led to the development of increasingly better mechanical devices for the measurement of time, driven by weights, gears, and springs from the 14th century onwards. However, the invention of pendulum clock in the 17th century marked a major breakthrough in mechanical timekeeping. At the left-hand side of this page, figure 8.6 is given. Figure 8.6 represents Huygens pendulum clock, which is a classic clock with a long rod. Children, at the bottom of this page, one more interesting box is given named as Know a Scientist, where students can learn about the contributions of Indian and international scientists related to the relevant topic. This box reads, "The pendulum clock was invented in 1656 and patented in 1657 by Christian Huygens, 1629 to 1695. He was inspired by the investigations of pendulums by Galileo Galilei, 1564 to 1642. It is said that once while sitting in a church, Galileo's attention was drawn to a lamp suspended from the ceiling, which was swinging back and forth. Using his pulse to measure time, Galileo found that the lamp took the same time for each swing. After experimenting with different pendulums, Galileo concluded that the time taken to complete one oscillation was always the same for a pendulum for a given length. Page number 109, 8.1.1, a simple pendulum. In this section, a dialog box is given on the right-hand side of this page where a boy is asking, "We did an activity in the chapter Measurement of Length and Motion in the grade 6 science textbook Curiosity, where we observed the oscillatory motion of an eraser hung with a thread. Is the pendulum similar to that?" A simple pendulum consists of a small metallic ball called the bob of the pendulum, suspended from a rigid support by a long thread as given in figure 8.7a. Figure 8.7, a simple pendulum. In figure A, there is a rigid support at the top. A long thread with a metal bob at the end is given. Figure B represents 3 positions of bob in a pendulum, which are mentioned or labeled here. Mean position in the middle. In the left and the right, the extreme positions are mentioned. The pendulum at rest is in its mean position. When the bob of the pendulum is moved slightly to one side and released, it starts oscillatory motion. Its motion is periodic in nature because it repeats its path after a fixed interval of time. The pendulum is said to have completed one oscillation when its bob, starting from its mean position O, moves to extreme position A, changes direction and moves to another extreme position B, changes direction and comes back to O, as given in figure 8.7b. The pendulum also completes one oscillation when its bob moves from one extreme position A to another extreme position B and comes back to A. The time taken by the pendulum to complete one oscillation is called its time period. Let us now set up a pendulum and measure its time period. Activity 8.2. Let us experiment. Step 1. Collect a piece of string around 150 cm long, a heavy metal ball with hook or a stone bob, a stopwatch or a watch, and a ruler. Step 2. Tie the bob at the end of the string. Step 3. Fix the other end of the string to a rigid support such that the length of the string in between support and bob is around 100 centimeter. Step 4. Wait for the bob to come to rest. Your pendulum is now ready. Page number 110. Step 5. Gently hold the bob, move it slightly to one side and release it. Take care not to push the bob while releasing it and that the string is taut. Is your pendulum now oscillating? Step 6. Using a watch, measure the time it takes for the pendulum to complete 10 oscillations. Record the time in table 8.1. Step 7. Repeat this activity 3 to 4 times. Step 8. Divide the time taken for 10 oscillations by 10 to calculate the time period of your pendulum. Note it down in table 8.1. Table 8.1. Time period of a simple pendulum. Length of the string is given as 100 centimeter. This table includes 3 columns. Column 1 is serial number. Column 2, time taken for 10 oscillations in seconds. Column 3, time period in seconds. In this table, 3 rows are provided for students to record their observations. Is the time period of your pendulum almost the same every time? What do you conclude from this observation? The time period of the pendulum is almost the same every time. Children, at the bottom of this page, there is another box, which is Think Like a Scientist. This box reads, You just did an important historical experiment which was first done by Galileo, except you used a watch to measure time in place of your pulse beat. Suppose you were Galileo experimenting with pendulums, what all would you investigate? What questions could you ask? Would all pendulums have the same time period? How would you test this? Repeat activity 8.2 using the same bob but with pendulums of 2 or 3 different lengths. Does the time period change? If so, how does the length affect it? If changing the length influences the time period, does the bob's mass also matter? Test this by repeating activity 8.2 with a fixed pendulum length but with bobs of different mass. Do you observe any change? The time period of a simple pendulum depends on its length but not on the bob's mass. All pendulums of the same length have the same time period at a given location. The time period of a simple pendulum of a given length is constant at a place. This property is used in the measurement of time. Page number 111. All clocks, old or modern, are based on some process repeating continuously, which can be used to mark equal intervals of time. Children, there is another interesting box named as Dive Deeper is given here. Let's read it. Modern clocks measure time using the same basic principle, periodically repeating processes, but use tiny and very rapid vibrations either from a quartz crystal or quartz clocks, or from some specific atoms, atomic clocks, while Huygens' early pendulum clocks could gain or lose 10 seconds each day. Today's atomic clocks are so precise that they lose only 1 second in millions of years. Scientists are constantly searching for even better ways to measure time with greater accuracy. At the middle of this page, figure 8.8 is given at the middle of this page, where some common clocks and watches are given. Let me describe them. In this figure, a big size pendulum wall clock is given, a circular wall clock, digital wristwatch, digital watch, and a stopwatch are given. 8.1.2 SI unit of time. The SI unit of time is the second. Its symbol is small s. The larger units of time are minute or MIN and R, small h. Children, here 2 boxes are given. One says 60 seconds is equal to 1 minute and the another box says 60 minutes is equal to 1 hour. Children, at the middle of this page, one more interesting box is given, which is named as Dive Deeper. This box contains advanced concepts that lead to questions for in-depth exploration of a topic. This box reads, units of time such as second, minute, and hour begin with a lowercase letter, except at the beginning of a sentence. Their symbols, small s, min for minutes, and small h are also written in lowercase letters and in singular. Note that a full stop is not written after the symbol except at the end of a sentence. While writing the time, always leave a space between the number and the unit. Also, note that writing SEC for second and HRS for hour is incorrect. At the bottom of this page, one more box named as Fascinating Facts is given. This box reads, the hole in the ball of Ghatika Yantra was made in such a manner that it took 24 minutes to fill and sink. The time unit measured by this clock was called Ghatika or Ghati. It became the standard unit of time measurement and continued until the end of the 19th century. A 24-hour-long day was thus divided into 60 equal ghatis. Page number 112. Activity 8.3. Let us identify. Look at the wall clock which is given in figure 8.9 carefully. Figure 8.9. Here a wall clock is given. What is the smallest interval of time you can measure with it? 1 second is the smallest interval of time that we can measure using this clock. Children, here a box named as Science and Society is given for you, which highlights the social connection and real-life applications. This box reads, in today's world, measuring tiny fractions of a second is very important. For example, in sports, timekeeping devices can record events down to 1/100th or even 1,000th of a second or a millisecond to determine the winners in a race. In medicine, heart monitors like electrocardiogram, ECG machines measure the millisecond variations in heartbeats to detect health issues. In music, digital recordings capture sound thousands of times per second for smooth playback. Many devices use even shorter intervals. Smartphones and computers process signals in microseconds, 1/1,000,000th of a second, allowing them to operate very fast. Scientists continue to develop even more precise time measuring tools for space exploration, medicine, and advanced science experiments. The faster and more accurate our clocks become, the more they help society in ways we may not even notice. Children, a dialog box is given at the middle of this page where a girl is asking, for races covering the same distance, we can tell who was faster by measuring time. But how can we tell that when comparing races for different distances? 8.2. Slow or fast. What do we mean when we say something is moving fast or slow? Suppose you are watching a 100-meter race on a straight track. All the players begin from the starting line together, but after some time they are not running together, which is given in figure 8.10. Figure 8.10 is given on the next page. We will discuss it later. How do you decide who is running faster amongst them? Page number 113. Children, at the top of this page, figure 8.10 is given. This figure represents 7 boys running a race on a straight track. One boy is ahead and others are behind. Someone who is ahead of others at some instant of time is running faster than them. Hence, someone who has covered more distance within the same time is running faster. The distances moved by objects in a given interval of time decide which one is faster or slower. We often say that the faster runner has a higher speed. You are probably familiar with the word speed. 8.3. Speed. By comparing the distances moved by 2 or more objects in a unit time, it can be found out which of them is moving faster. The unit time may be 1 second or 1 minute or 1 hour. We call the distance covered by an object in a unit time as the speed of the object. How can we determine the speed of an object? It can be calculated if we know the total distance covered by an object and the time taken to cover it. The speed of an object is the total distance covered divided by the total time taken to cover it. Thus, speed is equal to total distance covered divided by total time taken. What would be the unit of speed? We know the SI units of length and time. Since the speed is distance upon time, the SI unit of speed is meter per second and is expressed as m divided by s. Speed can also be expressed in other units. If we express the distance in kilometer and time in hour, then the unit of speed is kilometer per hour, expressed as kilometer divided by h. Page number 114. Example 8.1. Swati's school is 3.6 km from her house. It took her 15 minutes to reach her school riding on her bicycle. Calculate the speed of the bicycle in meter per second. Solution. Speed of the bicycle will be given as distance covered divided by time taken. It gives us 3.6 km divided by 15 minutes, which gives us 3.6 km into 1000 meter by kilometer. The whole is divided by 15 minute into 60 second by minutes. Here, kilometer is cancelling kilometer and minute is cancelling minute. This gives us 3.6 into 1000 meter divided by 15 into 60 second, which gives us 4 meter per second. Activity 8.4. Let us calculate. Step 1. Look up at the railway timetable on the internet. Step 2. Identify a train stopping at the railway station nearest to your place of stay. Find out the name of the next station where this train stops. Also, find the distance to that station as given in the timetable. 4. Note the time at which the train departs from your station and arrives at the next station. Find the difference to calculate the time taken by the train to cover the distance till the next station. 6. Calculate the speed of the train between the two stations and record it in table 8.2. 7. Repeat for 4 to 5 different types of trains: passenger or express or superfast. Table 8.2. Finding the speed of trains. Name of the railway station nearest to your place of stay. A blank space is provided for the students. Table 8.2 includes 6 columns. Column 1 is serial number. Column 2, name of the train. Column 3, name of the next station. Column 4, distance till the next station in kilometers. 5. Time taken till the next station in hours. 6. Speed of the train between these two stations in kilometer per hour. Children, 4 rows are given here to record your observations. Page number 115. Step 8. Compare the speeds of the trains. Which is the fastest train? The train which has covered the maximum distance in unit time is the fastest train. That is, the one with the higher speed. 8.3.1. Relationship between speed, distance and time. We already know how to calculate speed using the formula speed is equals to total distance covered divided by total time taken. If the distance travelled and time taken for it are known to us, we can write this equation in a different form to calculate the distance covered by an object if we know its speed and the time taken by using total distance covered is equal to speed multiplied by total time taken. Similarly, we can also calculate the time an object will take to cover a distance if the distance and speed are given by using total time taken is equal to total distance covered divided by speed. Example 8.2. Raghav is going to a neighboring city in a bus moving at a speed of 50 km per hour. If it takes him 2 hours to reach that city, how far is that city? Solution. Distance covered by bus is equal to speed multiplied by time, 50 km by hour into 2 hours, which gives us 100 km. Example 8.3. a train is traveling at a speed of 90 km per hour. How much time will it take to cover a distance of 360 kilometers? Solution. Time taken by the train is equal to distance covered divided by speed, which gives us 360 kilometer divided by 90 kilometer by hour, which gives us 4 hour. In all the examples so far, we have found the speed of an object by using the total distance covered divided by the total time taken. However, the object might not have traveled with the same speed during the entire duration of time. The object might have sometimes moved slower or sometimes faster. So, the speed that we have calculated is the average speed. But in this book, we have used the term speed for average speed. Page number 116. Children, at the top of this page, another interesting box named as Science and Society is given. This box reads, vehicles such as scooters, motorbikes, cars, and buses have an instrument which measures and displays the vehicle speed in kilometer per hour. It is called a speedometer. Another instrument, known as an odometer, is also fitted in the vehicles that measures the distance traveled by the vehicle in kilometer. In this box, a picture is also provided which represents speedometer and odometer in a vehicle. After this, a dialog box is provided where a boy is asking, I once watched a part of marathon on a straight rod stretch. I noticed that some people seemed to be running at the same speed during that distance, while some people would speed up or slow down. How were their motion different? 8.4. Uniform and non-uniform linear motion. Do you remember learning about linear motion in the chapter Measurement of Length and Motion in the grade 6 science textbook Curiosity? When an object moves along a straight line, its motion is called linear motion. Now, imagine a train on a track which is along a straight line between two adjacent railway stations. So, the motion of the train between these two stations is an example of linear motion, which is given in figure 8.11. Figure 8.11 is given at the bottom of this page, which represents a train on a straight track. The train starts from the first station A at a slow speed, then moves at a faster speed, then slows down and comes to a halt at the next station D. In between the two stations, for some distance B to C, the train moves at a constant speed, that is, at an unchanging speed. Page number 117. An object moving along a straight line with a constant speed is said to be in uniform linear motion. So the train is in uniform motion between B and C, as given in figure 8.11. On the other hand, if the speed of an object moving along a straight line keeps changing, it is said to be in non-uniform linear motion. The motion of the train between A and B as well as between C and D is uniform, as given in figure 8.11. Is non-uniform, which is given in figure 8.11. An object in uniform linear motion in equal intervals of time, while it covers unequal distances in equal intervals of times when it is in non-uniform linear motion. In table 8.3, data are given for the distances travelled by two trains X and Y between the time 10 am and 11 am. At the middle of this page, table 8.3 is given. Distances travelled by two trains in equal time intervals of 10 minutes. This table includes three major columns. Column 1 records time in equal intervals of 10 minutes. Column 2 and column 3 for train X and for train Y compares how two trains, train X and Y, move over time. Both of these columns, column 2 and column 3, are further divided into two sub-columns for recording about the position and distance by train X and Y. Let us listen to the readings provided in each of the column of this table. Column 1 records time in AM. Readings are: at 10 am, the position of train X at 0 km, distance is 0 km. For train Y, position 0 km, distance 0 km. At 10:10 am, position of train X is 20 km, distance 20 km. For train Y, position 20 km, distance 20 km. At 10:20 am, position of train X 40 km, distance 20 km. For train Y, position 35 km, distance 15 km. At 10:30 am, train X position is 60 km, distance 20 km. For train Y, position 50 km, distance 15 km. At 10:40 am, train X position 80 km, distance 20 km. Train Y position 75 km, distance 25 km. At 10:50 am, train X position 100 km, distance 20 km. For train Y, position 95 km and distance 20 km. At 11 am, train X position 120 km, distance 20 km. For train Y, position 120 km, distance 25 km. Which of the two trains is in uniform linear motion between 10 am and 11 am? Train X covers equal distances in equal intervals of time, so it is in uniform linear motion, while train Y is in non-uniform linear motion. Uniform linear motion is an idealization. In everyday life, we seldom find objects moving with a constant speed over long distances or for long intervals of time. That is why we have to use average speeds. Page number 118. Before coming to the next section, let me describe a beautiful picture presented at the left-hand side of this page. There is a cheerful boy standing inside an open walnut shell. He is holding a paper with some notes on it. This picture is symbolizing the idea of summarizing the chapter. So, the name of the next section is In a Nutshell. Point number 1. The time taken by the pendulum to complete one oscillation is called its time period. 2. The time period of a simple pendulum of a given length is constant at a place. 3. The SI unit of time is the second. Its symbol is small s. 4. The average speed of an object is the total distance covered divided by the total time taken to cover it. 5. An object moving along a straight line with a constant speed is said to be in uniform linear motion. 6. If the speed of an object moving along a straight line keeps changing, it is said to be in non-uniform linear motion. Now, let us describe an illustration given on the left-hand side of the next section. Here, an illustration of a girl is given who is encouraging us to participate in this section. The girl is sitting confidently on a block with a question mark written on it. She is holding a word block named as inquiry. She is climbing through a rope and blocks. These blocks are shaped like a big stone and has a question word written on it. These words are why, what if, where, when, how long, what could, can it, which, whose, what else, what will happen, why not, what should. Children, this picture reminds us to keep asking questions and to learn better. Let us move to the next section now, which is named as Let us enhance our learning. Question number 1. Calculate the speed of a car that travels 150 meters in 10 seconds. Express your answer in kilometer per hour. Question number 2. A runner completes 400 meters in 50 seconds. Another runner completes the same distance in 45 seconds. Who has a greater speed and by how much? Question number 3. A train travels at a speed of 25 meter per second and covers a distance of 360 kilometer. How much time does it take? Question number 4. A train travels 180 km in 3 hours. Find its speed in first, kilometer per hour, second, meter per second, third. What distance will it travel in 4 hours if it maintains the same speed throughout the journey? Question number 5. The fastest galloping horse can reach the speed of approximately 18 meter per second. How does this compare to the speed of a train moving at 72 km per hour? Question number 6. Distinguish between uniform and non-uniform motion using the example of a car moving on a straight highway with no traffic and a car moving in city traffic. Question number 7. Data for an object covering distances in different intervals of time are given in the following table. If the object is in uniform motion, fill in the gaps in the table. Let us describe the table given in this question. Row 1 records time in seconds. Row 2 records distance in meter. When time is 0 seconds, distance is 0 meter. When time is 10 seconds, distance is 8 meter. When time is given as 20 seconds, the blank space is provided for students to record distance in meters. Time is 30 seconds, the distance is 24 meter. A blank space is provided for recording time in seconds when the distance is 32 meter. Next, when time is 50 seconds, distance is 40 meters. For the next, time and distance are not provided. Blank space are provided for the students to record time in seconds and distance in meter. For the next reading, time is 70 seconds and distance is 56 meters. Page number 119, question number 8. A car covers 60 km in the first hour, 70 km in the second hour and 50 km in the third hour. Is the motion uniform? Justify your answer. Find the average speed of the car. Question number 9. Which type of motion is more common in daily life, uniform or non-uniform? Provide 3 examples from your experience to support your answer. Question number 10. Data for the motion of an object are given in the following table. State whether the speed of the object is uniform or non-uniform. Find the average speed. Children, here is a table. Let us describe this table. The first row records time in seconds and the second row records distance in meters. When time is 0 second, distance is 0 meter. When time is 10 seconds, distance is 6 meters. Time 20 seconds, distance 10 meters. Time 30 seconds, distance is 16 meters. Time 40 seconds, distance 21 meters. Time 50 seconds, distance is 29 meters. Time 60 seconds, distance is 35 meters. Time 70 seconds, distance 42 meters. Time 80 seconds, distance 45 meters. Time 90 seconds, distance 55 meters. Time 100 seconds, distance is 60 meters. Question number 11. A vehicle moves along a straight line and covers a distance of 2 km. In the first 500 meter, it moves with a speed of 10 meter per second and in the next 500 meter, it moves with a speed of 5 meter per second. With what speed should it move the remaining distance so that the journey is complete in 200 seconds? What is the average speed of the vehicle for the entire journey? Before coming to the next section of this page, let me describe a beautiful illustration which is provided at the right hand side of this page. Here is an image where a smiling boy is climbing up step by step through a rope ladder. Each step of the ladder represents a word like curiosity, exploration, inquiry, discovery, and innovation. Children, this picture is indicating that these steps lead to innovation. So let us move to the next section, which is exploratory projects. First, construct a floating ball type water clock. Experiment by using balls of different sizes and making holes of different sizes in them so that the sinking time of the ball can be close to 24 minutes. Second, Design an activity for measuring the pulse rate, number of times the pulse of a person beats in 1 minute of your friends. Think of an activity where you can use your pulse to measure time and develop a story over that idea. Third, what might be the reasons for the slight differences in the time periods of a pendulum of a given length in different readings taken in Activity 8.2? Think of ways to control those and repeat the activity to check if the difference in readings is reduced. Fourth, visit a playground with a few swings. Measure the time taken by a swing for 10 oscillations and calculate its time period. Repeat it a few times with children of different weights to find out if its time period is almost the same. Repeat this with swings of different lengths. Find out how the time period changes with increasing length of the swings. Is the swing also an example of a pendulum? Page number 120. Fifth, gather the timings of the winners of the races 100 meter, 20 meter and 400 meter for men and women in the last 2 Olympic Games. Calculate and compare their speeds. In which event is the speed the fastest? Children, at the left-hand side of this page, an illustration is given. Interdisciplinary zigzag rope chart is provided here, which is depicting that all the areas like history, art, geography, society, technology, and economy are integrated. Now, there is an interesting box, Fascinating Facts. This box reads, time started when our universe was created and will continue in the future. We cannot see or feel time, but we can only measure its passage in terms of a time interval between the events. These time intervals can be fractions of a second, or even days or months, or years or centuries. We can only say when an event occurred or for how long it lasted. Though we have learned to measure time with increasing accuracy, and our lives are governed by watches and clocks, what is time continues to be a tricky question with no easy answer. This chapter ends here.
Curiosity. You were just listening to this audiobook. Textbook of Science for Grade 7. Narration Harsh Priya. Sound recordist Virendra Rawat. Production assistant Mohammad Shamim Khan. Directed and produced by Vimalesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.